65 million years ago, an asteroid crashed into Mexico and triggered a mass extinction event that would kill off the dinosaurs. We all know that one, but a lot less of us know that an even bigger asteroid landed in the Sudbury region of Canada nearly 2 billion years ago and left behind massive amounts of precious metals from space inside the Earth's crust. And just a few 100 million years before that, an even bigger asteroid landed in Vredefort, South Africa. It created the largest known impact crater on the surface of the Earth today. Lucky for us, it's been a very long time since one of these Earth-shaking monsters has come our way. Which begs the question, are we lucky, or does that mean we're overdue for an extinction-level event? The closest asteroid encounter that we've had in the modern day actually happened in 2013. A relatively small rock, about the size of a house, came screaming through Earth's atmosphere at a speed of over 69,000 kilometers per hour and lit up the skies over northern Russia. This asteroid almost landed in the Chelyabinsk region of Siberia, but before it could reach the ground, the rock itself exploded due to a buildup of heat and pressure at an altitude of roughly 30 kilometers. But that doesn't mean the Earth was safe. A resulting shockwave ripped through the air with enough power to shatter glass windows and crumble brick walls. As many as 1,600 people were injured, and over 7,000 buildings were damaged across 6 cities. Now, we're lucky to say that the 2013 asteroid could have been worse. If it had exploded any closer to the Earth, the damage would have been greatly amplified. So let's take a look at what happens when an asteroid strikes the surface of a planet. Let's use a big one, just for fun. The rock that took out the dinosaurs was about 10 kilometers wide, and we have a pretty good idea what happened on the day that thing landed. Now this is a lot different from getting hit with a bullet or a cannonball or any other traditional impact. These space rocks operate more like underground bombs. So, assuming our solid massive asteroid survives its blazing hot journey down through the atmosphere, in the instant that it makes contact, it's going to punch through the surface, and then it's going to release its kinetic energy into the Earth. That is the energy of an object in motion, which is mass times velocity squared, and we are talking about a very heavy object moving at tens of thousands of kilometers per hour. The release of that energy is going to vaporize the asteroid itself, so the whole giant space rock instantly transitions from a solid into a gas. That means rapid expansion, also known as explosion. The explosion will radiate out in all directions. Above ground, that looks like a devastating shockwave and fire that incinerates everything as far as the eye can see. That sucks for everyone inside that blast zone, but this is not the real problem with asteroid impacts, because just as much of that energy from the explosion is going to be directed underground, and for every action there's an equal and opposite reaction. So what happens is the ground itself gets launched up into the air. That one big rock from space has now sent thousands of smaller rocks flying out in all directions. And they're not going to carry enough velocity to go all the way to space, but they are going to be moving fast enough to enter these suborbital trajectories. And the most powerful of the ejected rocks will fly halfway around the world to rain destruction on every continent of the Earth. That's how you end up with a global extinction event. The sky literally becomes fire and smoke and ash, and no matter where you are in the world, it's like being caught inside an oven. So either a chunk of rock lands on you, or you live long enough to be cooked alive. Either way sucks. Unless you live underground or underwater, in which case you have to wait out an ice age for your opportunity to repopulate the Earth. When you hit play on an episode of The Space Race, what you're really seeing is the end of a long, complicated process. Every video goes through multiple people doing research, writing, multiple rounds of editing, motion graphics, 3D work, animation, asset tracking, timelines, and constant coordination to keep everything moving in the same direction. Sintra.ai helps us manage the operational side of that process. Instead of a single do-everything AI, Sintra gives you focused AI helpers that work like virtual teammates, each designed for a specific job. We've been using helpers like Gigi to keep episodes organized as they move from early concepts to the final cut, tracking tasks, managing handoffs, and making sure nothing gets lost as files and timelines evolve. On the business side, we're also using Emmy, Cintra's email marketing helper, to support our merch shop by building and organizing email flows for launches, restocks, and ongoing campaigns. And this isn't about replacing creative work or technical skill. Editing, animation, and visual storytelling still depend on real people. What Cintra does is cut down on friction, keep everything structured, and give the team more time to focus on execution instead of logistics. All of that lives in one simple platform that's there whenever you need it. So go to cintra.ai/spacerace or use code SPACERACE to get an exclusive 72% off all plans with a 14-day money-back guarantee. Thanks again to Cintra.ai for supporting the channel and helping keep the space race running smoothly. Going back now to our modern day Siberian asteroid, obviously it could have been a lot worse, but inevitably the day will come when it is worse. So what happens to us on that day? Well, it largely depends on how prepared the human race is to meet this doomsday rock. You see, the problem is we're not as good at spotting asteroids as you might think or hope. For example, the 2013 Siberia asteroid literally took the world by surprise. No one saw that coming until the people on the ground looked up and saw it with their own eyes just seconds before the explosion. To understand how something so nearly catastrophic can just slip through the cracks, you need to see something. This is an image from the European Space Agency that plots the location of every known near-Earth object, which is a title that we give to anything that will come within about 45 million kilometers of the Earth's orbit. So most of these dots are currently nowhere near the Earth, but all of them will come close at some point on the timeline. How close? Well, that's the thing that we're constantly trying to figure out. You might remember an asteroid scare in February 2025 that gripped the news media for a couple of weeks. That was one of the rare occasions where a newly discovered object appeared to have a chance of impacting the Earth within a relatively short time. The asteroid in question was somewhere between double to 4 times the size of the 2013 Siberian event, so it had potential to do significant damage. Not world-ending, but a very, very bad day for any city or town that it happened to land on. And that day would arrive as early as 2032. Now, the chance of impact was never higher than about 3%, which doesn't sound like much, but another way to say that would be about 1 in 33. How lucky are you feeling? Fortunately for us, the chance of impact with the Earth eventually dropped to 0, although the odds of hitting the moon then rose to about 4%, and while that's better than the Earth getting hit, you don't want an asteroid crashing into the moon either. Imagine the same impact scenario we played out earlier happening on the moon instead. Of course, no people would be caught up in the blast zone, so that's good, but because the moon has only about 1/6 the gravity of the Earth and no atmosphere to slow things down, this time a lot of the ejected debris will actually make it all the way into space. So now the moon is essentially creating a big trail of rubble as it orbits around the Earth, kind of like a ring, which is cool, except because the explosion released energy in every direction, a lot of that debris is going to be headed towards us. Now, the asteroid that might hit the moon is a lot smaller than the one that caused the dinosaur extinction, so the chunks of rock that get ejected from the moon will also be on the small side, meaning that our atmosphere will catch pretty much everything that makes its way over, and it will just burn up. The real danger is actually to all of our satellites and anything else that might be orbiting the Earth in 2032, because that stuff is going to get a shower of debris and dust from the moon, and that would cause problems. Don't expect Google Maps to work after that one, or Starlink, or anything else dependent on a satellite network. But how do we even claim to know stuff like this in the first place? Well, let's talk about how these predictions get made and why very dangerous objects like the fireball in the Russian sky are able to slip through the cracks. The most effective way to find an asteroid is to simply point a camera at the night sky and take a series of photos over a relatively short timeline, like a few hours. As long as we account for the Earth's rotation, we know that the stars will remain still over that time, so now we look for anything that moves in between the photos. Up until very recently, it's been impossible to photograph the entire night sky at the same time. So what we've been relying on is a small group of dedicated individuals all around the world who spend their entire night looking at photos of white dots on a black screen. Now, let's say they do find something new. Let's say it's an asteroid the size of a football stadium. How do we know if this object is a threat? Well, in simple terms, you look at where the object was when it was first detected, then you look at where it is now, and you draw a line connecting the 2 points, because everything in the solar system orbits around the sun. That line is going to curve, and then to see where the asteroid is going, you follow the curve and draw a prediction. Of course, the exact shape of that line is going to involve a lot of complicated factors of orbital mechanics that we're not going to worry about today. But an easy way to picture this would be the first prediction is going to be drawn with a very wide brush, much wider than the path of the actual asteroid, but because we still have limited information, we have to account for the potential margin of error. And this is how we end up with an asteroid scare that dominates global headlines, because if the Earth happens to be inside that wide brushstroke, then at that time, there is a chance that we end up in the final path of the object. But what happens is that over time, the observers get more information about how the asteroid is moving, and gradually they redraw the line with a thinner brush. Now, the scary thing is, if the line gets thinner and the Earth is still inside that line, then our chances of getting hit will rise. Sometimes they rise by a lot. This is not a time to panic though, because the most likely outcome is always that the line will get thinner and thinner until the Earth is no longer inside the path of the object, at which point our chance of impact goes straight to zero. So it's understandable that the average person would get very confused by this process, upset even. But if you understand what's going on, then hopefully that saves you some doomsday prepping the next time this news story comes around, because it will happen again, and it will happen more often as time goes by. The good news is that we're pretty sure we've located at least 99% of all the extinction level near-Earth objects. Those are rocks about 10 kilometers in diameter or more, and none of them are going to hit us, not anytime soon at least. The problem when we draw that line of prediction is that we can get it down to such an ultra-thin trajectory that we know exactly where it's going to go, but the line itself can never be drawn more than about 100 years into the future. Those complicated variables of orbital mechanics that we mentioned earlier start to make the predictions less accurate after a certain point until prediction becomes simply impossible. Either way, you shouldn't worry about doomsday rocks, because even if we did see one coming at any time soon, there's nothing we can do to stop it, not unless we invent a powerful new measure of planetary defense. And we might. But personally, after looking into this, I'm much more worried about the smaller ones. Did you know that in the past 40 years, there have been over 1,200 asteroids with a size larger than 1 meter that have hit the Earth's atmosphere? Probably not, because out of all of those, less than 10 were actually detected before they hit, and even when they were spotted, it was about 1 day of warning at most. If you're wondering how that can happen, just think back to our dedicated team of insomniacs. They're looking for dots on screens. They can only see objects that are either really big or really bright. If the asteroid doesn't reflect enough sunlight, then it's practically invisible to the camera. And probably worst of all, we know that this leaves us with a giant blind spot in our asteroid detection, because we can't point a camera at the sun. Its brightness washes out everything else in the frame. So an asteroid flying at us from the direction of the sun would be essentially undetectable. Of course, the space between the Earth and the sun is much smaller than the space outside of the Earth's orbit, so how likely could it be that we get something from that direction? Well, the 2013 Siberia asteroid came at us from the sun, so unfortunately, it's not uncommon. And just like our giant extinction-level asteroids, it's really not worth worrying about these things either, because again, there's not anything that anyone is going to be able to do about it. Now, there is a sweet spot of an asteroid that we should be worried about. That's something in the range around 1 kilometer in width, give or take. Small enough that they might still be undetected, but big enough that we could reasonably spot one 10 or 20 years in advance of a direct hit. So, what do? An asteroid around 1 kilometer in diameter would not cause a global extinction, but it would annihilate an entire country the size of Germany or France. And we can probably all agree that something like that should be stopped from happening, if such a thing were even possible. And we do have some ideas. One is to simply crash into the asteroid and try to nudge it off course. This is one that NASA has already experimented with. The Double Asteroid Redirection Test, also known as DART, was launched in 2021. It would send a probe about the size of a porta potty on a direct collision course with an asteroid called Dimorphos, which itself is about 177 meters across, large enough to decimate a major city if it happened to land on one. This is what it looked like when DART hit that asteroid in September 2022. We chose this asteroid because it actually orbits around a much bigger asteroid called Didymos. Not that Diddy. But what we were looking for was a change in that orbit of one asteroid around the other, because that's much easier to measure than a change in orbit around the sun. What we've observed in the years since then was a complete success. The DART impact moved Dimorphos into a different orbit around Didymos, and the amount of change actually far exceeded NASA's expectations. The impact was about 30 times more effective than the baseline prediction. So that's a positive result, but it's still inconclusive about how we could actually change the path of a 1 kilometer sized rock over the course of 10 or 20 years orbiting around the sun. We could theoretically launch an impact that is a bit bigger than DART someday, but for the near future, there's going to be a limit on what we can fit inside a rocket, and it's not very big. Not in comparison to a city-destroying asteroid, at least. But one thing that we can look forward to in the short term is a lot more knowledge about near-Earth objects, and knowledge is power. There's a new telescope that just came online in 2025 that's located in the Chilean desert at a site called the Vera Rubin Observatory. Remember we talked about the guys staring at little pictures of the night sky and said that it was impossible to photograph the entire night sky all at once? Well, now it is possible, thanks to this telescope. Not only is it really big and really powerful, it's also very nimble, so using a system of high-precision electric motors and stabilizers, the Vera Rubin Observatory can move fast to take many pictures of many locations all in one night. It essentially lets us take a detailed survey of the entire visible sky once or twice a week. That essentially lets observers create time lapses of the universe, and then within that moving picture, we look to identify the fastest moving objects. So as a result, we are going to find a lot more near-Earth asteroids, and that is going to be a scary time for a lot of people. But at least now you know what exactly to be worried about, and even if there is a cause for concern, it might not be the end of the world as we know it.